Hello everyone. This is the review video for the Unit 4 review. This is actually quite a short review. I think your unit was pretty short as well. This is on nuclear reactions. Okay, so you looked at three types of nuclear reactions in this unit. You looked at nuclear fission, nuclear fusion, and radioactive decay. Okay, so nuclear fission is when you take one species, one thing, one nucleus in this case, and you split it into multiple parts. Sometimes it's 2 pieces, sometimes 6 pieces fly off. But when you get more nuclei than you started with, that is called fission. Fission, just the word fission, means to break apart. Nuclear fusion, think of fusing something together, is when you take multiple nuclei and they join and form one nuclei. Okay? Nuclear fusion also produces a tremendous amount of energy in the process of fusing. Okay? Whereas in nuclear fission, you actually need to provide the environment with a ton of energy in order to split the nuclei into multiple nuclei. Okay? And then radioactive decay, when some elements that are rather heavy and quite unstable, when given enough time, that nucleus will, what we call decay. In other words, it will break down into a smaller, more stable nucleus. And in the process, it emits a particle. Sometimes it's an alpha particle, sometimes it's a beta particle, and sometimes it's a gamma particle. Okay? So nuclear fission is breaking a nucleus into multiple nuclei. Nuclear fusion is joining nuclei to form a bigger element, or heavier, I'll say, and radioactive decay is the spontaneous breaking down of a nucleus. All right, and you can see in the pictures here some examples. Nuclear fission is how they produce energy from nuclear reactors. It's the bombardment, basically, of a uranium atom with particles to split the uranium into smaller pieces. Nuclear fusion is what's happening on the sun. Okay, hydrogen atoms are combining at very, very, very high temperatures and energy to form helium, and in the process releasing a ton of energy, and that energy is what's fueling the sun. And radioactive decay, we use, the most common one is carbon-14 dating. Every living species has a certain amount of carbon-14 in their bodies, in their anatomy. And the carbon-14 decays after that living species dies. And so you can detect the amount of carbon-14 in a fossil and know how long something has been, how old the fossil is, or how long ago they were alive. Okay, so these are the objectives: describe and compare nuclear fusion and nuclear fission, differentiate between chemical and nuclear reactions, identify some applications of fusion and fission, describe and compare different forms of radioactive decay, and then explain the concept of half-lives. So we'll get to that. This first activity says forces exist among the protons, neutrons, and electrons that make up an atom. Sometimes these forces make atomic nuclei unstable. Use the activity to review nuclear forces. Okay, so which kind of force could hold an atomic nucleus together? So think about it. Opposite charges attract, like charges repel. And when you're talking about an atom, we know that the proton and the neutron live inside the nucleus, and the electron lives outside the nucleus in the electron cloud. Okay? So knowing that, your options are a force that pushes 2 protons apart Do you think that would hold an atomic nucleus together? A force that pushes two electrons apart, a force that holds protons and neutrons together, and a force that holds electrons and protons together. Okay, so give it your best shot in terms of guessing and see where it takes you. Now, isotopes. Isotopes are different versions of the same element, right? Isotopes have the same atomic number, they just have a different number of neutrons, which makes their mass different. So for example, there's 3 different common isotopes of hydrogen. Okay, there's hydrogen 1, hydrogen 2, hydrogen 3. Hydrogen 1, 2, and 3 all have 1 proton. That's what identifies them as hydrogen. But hydrogen 1 has no neutrons. Hydrogen 2 has 1 neutron, and hydrogen 3 has 2 neutrons. Those are isotopes of hydrogen. Okay? What is the mass number of an atom of oxygen with 8 protons and 9 neutrons? So to find the mass number, you will add those 2 numbers together. All right? And you can always get those numbers from the periodic table that they show you here. All right, this mass number, 47.87, that is the average of all of the isotopes of that element, okay? All right, fission and fusion, we talked about this a little bit ago. Changes in atomic nuclei can be classified as fission or fusion. Use the activity below to review the characteristics of each, okay? So remember, fission is breaking apart. Fusion is fusing together, bringing together, making one thing out of multiple nuclei, okay? So large nuclei splitting into smaller ones, that would be fission, okay? So I'm not going to do these for you. I'll get you started, and then you'll go through and do these on your own. Isotope notation. All right, so when we indicate an isotope, we use notation that looks like this, okay? So the bottom number means something and the top number means something, all right? So this says this helium atom has a nucleus of 2 protons and 2 neutrons. So think about, what is the mass of this helium atom? If I have 2 protons and 2 neutrons, I will have a mass of 4, okay? Which symbol is the correct way to write this isotope of helium? So the bottom number is the atomic number. It's the number of protons. It's the thing that identifies the element, all right? And the top number is the mass number. So from that, you should be able to choose the correct answer there. And then you looked at writing nuclear reactions. So what you have to be careful with in nuclear reactions is that the total mass is equal on the left and the right. Both the top and the bottom numbers have to be equal on the left and the right. Okay, because if they're not equal, then you have not abided by the law of conservation of matter. All right, you can't lose matter. That's what this says. Nucleons, protons, and neutrons is conserved. When writing the equation for a nuclear reaction, add up the number of nucleons on each side to ensure the 2 sides are balanced. Okay, so which reaction follows the conservation laws for nuclear reactions? So here I have 231. All right, on the right side, I have 227 plus 4. Does that equal 231? Okay, 91, 2 plus 89. If you look at choice B, 231, is that the sum of 4 plus 229? 91, is that the sum of 2 plus 87? So if both of those things are not true, then it does not abide by the law of conservation. All right? Okay. Comparing alpha and beta decay. So you looked at the particles that are emitted when nuclear fission happens. Alpha particles and beta particles are 2 examples of particles that are emitted during radioactive decay. So alpha particles are pretty heavy. they are basically a helium nucleus without the electron, right? So they are, if we go back to look at helium, oh, right there, okay? It's just this part of the nucleus is called an alpha particle, all right? It has a mass of 4 and a proton number of 2. Beta particles are much, much smaller. Beta particles are basically electrons, okay? So knowing that, see if you can go through and choose the right ones for all of these. Obeys the law of conservation of nucleon number, can involve the loss of an electron, I just said it, can turn a neutron into a proton. So these are back in your Unit 4 study. Make sure you go back and look at what is the difference between alpha particles and beta particles, okay? All right, determining the type of radioactive decay. Each type of radioactive decay changes an atom's nucleus in a certain way. By comparing the parent and daughter nuclei, you can determine which type of decay occurred. So let's take a look at this one. I have 210 here and 206 here. That means my question mark particle has to have a mass of, I hope you said 4, because 4 plus 206 will give you 210, okay? My atomic number here is 83, and this is 81. So my question mark has to have an atomic number of 2, right? So a 4 at the top and the 2 at the bottom is actually the element helium, but it is the particle alpha decay, okay? Finally, you looked at half-life. Half-life is the amount of time it takes. It is a measure of time. It's the amount of time it takes for half of an isotope to break apart and decay, okay? Each isotope has a different half-life. For example, the half-life of carbon-14 is like 5,400 years. Okay, the time it takes for half of the nuclei in a sample to decay is the half-life. It says the half-life of sodium-24 is 15 hours. If you start with 8 atoms of sodium-24, how many atoms will you have after 15 hours? Okay, so after the first 15 hours, half of the sodium that you have will be gone. Half of the sodium that you have will be gone, okay? So I think you can answer that question from there. Okay, that is it. If you have questions or you don't understand something in this unit, please shoot me an email. We can jump on Zoom and work it out together. All right, have a great day.